The quantum model of the atom. In 1924, French scientist Louis de Broglie suggested that electrons be considered waves confined to a space around an atomic nucleus. These waves could only exist at certain frequencies, which correspond to specific energies. Diffraction refers to the bending of a wave as it passes by the edge of an object or through a small opening. Interference occurs when waves overlap. This results in a reduction of energy in some areas and an increase of energy in others. This idea of electrons being both particles and waves troubled scientists. However, in 1927, German theoretical physicist Werner Heisenberg proposed the Heisenberg uncertainty principle. This principle states that it is impossible to determine simultaneously both the position and velocity of an electron or any other particle. In 1926, Austrian physicist Erwin Schrödinger used the idea that electrons have a dual wave-particle nature to create an equation known as the Schrödinger equation. This equation treated electrons in atoms as waves. This equation, along with the Heisenberg uncertainty principle, laid the foundation for modern quantum theory. Quantum theory describes mathematically the wave properties of electrons and other very small particles. Solutions to Schrödinger's equation are known as wave functions. Electrons exist in certain regions called orbitals. An orbital is a three-dimensional region around the nucleus that indicates the probable location of an electron. To describe orbitals accurately, scientists use quantum numbers. Quantum numbers specify the properties of atomic and the properties of electrons in orbitals. There are for quantum numbers, principal quantum number, angular momentum quantum number, magnetic quantum number, and spin quantum number. The principal quantum number, symbolized by n, indicates the main energy level occupied by the electron. Values of n are positive numbers from 1 to 7. As n increases, the electron's energy and its average distance from the nucleus increases. L more than one electron can have the same n value. These electrons are in the same electron shell. The total number of orbitals in a given shell or main energy level is equal to Na. Orbitals of different shapes that exist for a given value of n are known as sublevels. The angular momentum quantum number, symbolized by L, indicates the shape of the orbital. For a specific main energy level, the number of orbital shapes possible is equal to n. The values of L are 0 and all non-zero integers less than or equal to n1. Depending on its value of L, orbitals are assigned a letter S, P, D, or F. In the first main energy level n equals 1, there is only one sublevel possible n-s orbital. The second main energy level n equals 2 has two sublevels, s and p orbitals. The third main energy level n equals 3 has three sublevels, s, p, and d orbitals. The fourth main energy level n equals 4 has for sublevels, s, p, d, and f orbitals. An nth main energy level has n sublevels. The magnetic quantum number, symbolized by m, indicates the orientation of an orbital around the nucleus. Values of m are integers, including 0, from L to plus L. The orientation of the s orbital corresponds to m equals 0. Therefore, there is only one s orbital in each s sublevel. There are three p orbitals in each p sublevel: px, pi, and pz. These three p orbitals are related to m equals -1, m equals 0, and m equals +1. There are 5 different d orbits in each d sublevel. These 5 d orbitals are related to m equals -2, m equals -1, m equals +1, and There are 7 different f orbitals in each f sublevel. The number of orbitals at each main energy level equals the square of the principal quantum number, n2. The fourth quantum number, the spin quantum number, has only two values L plus 1/2 minus 1/2, which indicate the two fundamental spin states of an electron in an orbital. The two electrons in a single orbital have to have different spin states.